Wow, the atomic bomb is the most dangerous weapon on Earth. How did the atomic bomb come to be?
That's an amazing question you ask.
What? Where did you come from?
I'm one of the people who worked on the Manhattan Project.
Yeah, but how are you still alive?
I'll answer that after I answer your question. First, we need a quick history lesson. The nuclear bombs work on an atomic scale. How do we even discover atoms? Well, Democritus, a Greek philosopher as you can see here, from the 2nd century BCE, was first to suggest the atomic theory, that everything is made up of these tiny building blocks called atoms. He also suggested that all these atoms are alike, and then for a long 2,000 years, nothing really advanced until John Dalton expanded and proved the atomic theory.
Oh, wow. I never realized how long we have been studying the atomic theory.
Yep. It indeed takes a long time and a lot of smart people to advance the field of nuclear science so that we can even begin to develop a bomb. But anyway, back to the lesson. Next, John Dalton expanded Democritus' theory. Everything is made up of small building blocks by saying that each element's tiny building blocks, atoms, look the same as each other, but atoms of different elements had different sizes and weights. He also stated that the atom is the smallest unit of matter.
So basically what Democritus stated was not the complete picture. John Dalton added on the theory by theorizing that these atoms looked the same but were different for each element by size and weight.
Alright, let's look at the next picture. So I'm glad you understand this, but it's still not the complete picture. There are more scientists and theories that added on to the atomic theory. The next one being is J.J. Thomson. J.J. Thomson was an English scientist who was born in 1856. He studied cathode rays mostly and added on to the theory by saying that all matter is made up of very, very tiny particles that are smaller than atoms. These particles are now known as protons, neutrons, and electrons. J.J. Thomson was most famous for discovering the electron. The idea that an atom was made of a big positively charged sphere with negatively charged particles dotting the interior of the sphere. He made this model and called it the plum pudding model. He discovered this by making his own experiment called the cathode ray experiment. It consisted of a vacuum tube with two metal plates inside of it. When electricity was passed through the metal plates, a cathode ray appeared and went straight down the middle of the tube. When a magnet was placed near it, it would move towards the positively charged of the magnet and away from the negative side of the magnet, which proved the cathode ray was negatively charged. We know that the cathode ray is made up of electrons, which are 2,000 times smaller than hydrogen atoms. This disproves Dalton's theory that the atom is the smallest unit of matter. The discovery of the electron and its charge and its capability to get lost lead to the invention of electricity, since electricity it just lost electrons bouncing off each other in a circuit until they reach the end of the circuit where, like a light, will be found and powered.
So we've talked about the atoms, and how they're different from each other and what particles they're made of and their charges. Is that it?
Not even close. We couldn't have come close to making a nuclear bomb with just this knowledge. We still have a few more topics to talk about. Next is Ernest Rutherford. Rutherford was born in New Zealand in 1871. He was a physicist who studies the nucleus by using the gold foil experiment.
Wait, what? Gold foil experiment?
Yeah, the gold foil experiment. It consisted of alpha particles being shot at a sheet of gold from which most particles passed right through, but some got deflected.
Oh, wait. Why were they deflected?
Good question. The reason that these particles were deflected off the gold foil is because they were the nucleus of the heat of helium. The nucleus is positively charged, so it bounced right back when it hit the gold foil's nucleus. But since most of the particles went right through, it led Rutherford to conclude that the nucleus was made of mostly empty space, and thus he discovered the nucleus through his experiment. With the discovery of protons, proton therapy is used to treat some cancers and tumors. A beam of proton is used to destroy the cancer cells. It is used when cancer has not spread greatly. It's typically used in serious parts of the body because it can be accurately aimed.
Wow, that's a lot of information to take in. How many more of these scientists will you teach me about?
Alright, there's a few more, but I'll make them shorter for you. After Rutherford discovered the nucleus, someone named Robert Millikan measured the electrons had a negative charge through something called the oil drop experiment. He observed and measured the speed of these droplets fell between two metal surfaces and without voltage. After him came Niels Bohr, who discovered the theory that the energy of hydrogen atoms is transferred only in certain well-defined quantities. Next came Russian scientist Dmitry Mendeleev, who found the periodic table. He arranged the elements in order of increasing atomic weight. I've always found him cool because he designed the table before all the elements were discovered, that there are a lot of blanks which were later filled in as more elements were discovered. Afterwards came Henry Moseley, who created Moseley's law by using Bohr's model, which stated that frequencies are proportional to the squares of whole numbers that are equal to the atomic number plus a constant. This equation was used to find the energy given off when electrons changed orbitals. Afterwards, chemist Max Planck discovered the energy quanta in 1918.
Is that it? Are we done?
Those are all the major scientists and their accomplishments, but there are still a few principles and theories that helped develop the bomb.
Okay, let's hear it.
Alright, the first one is the uncertainty principle theorized by Werner Heisenberg and Erwin Schrödinger. It is represented by the quantum mechanical model. This principle states that the momentum and position of a particle cannot be accurately determined at the same time. Basically impossible. Next one is the wave theory, developed by Louis de Broglie. It proposes that particles can have wave-like properties when traveling through space. This was later proved by the dual wave particle nature of light. Developed by Thomas Young, it was proven by passing light through one small pinhole and then two other pinholes. When the light hits the screen, it forms concentrated areas. The experiment thus proves that dual wave particle nature was real because it's being a particle and a wave at the same time. Next ones are rules and principles that are used in orbital notation and electron configuration. First, Aufbau's principle states that in an atom's ground state, electrons will go into the lowest energy levels before occupying higher levels. This is related to the Pauli exclusion principle because no two electrons can have the same four quantum numbers, so electrons will go elsewhere. Next one is Hund's rule. Every orbital in a subshell is singly occupied with one electron, for any one orbital is doubly occupied. And all electrons in a singly occupied orbital have the same spin. And the last one is, actually, that's just the last one.
Finally. So that's cool and all, but how does this relate to the nuclear bomb?
All this information combined helped develop the bomb. By understanding how all information ties in together, scientists could use it and make the atomic bomb.
Oh, alright, cool. So, do you mind telling me how you're still alive?
I don't know why I'm still here, but I think that being around all that radiation making the bomb might have something to do with it.
You should probably check that out.
Maybe.